So today's video is going to be about communication. Communication. But we will be talking about quantum communication. Quantum communication. And by quantum communication, I mean instead of why first of all why we want to make quantum communication a common thing in this world, because quantum communication is more secured. It's better than the communication we have in right now, the other in old times. Now communication is hackable, or is can be viewed by a third person, can be interrupted by third person. Okay, if I want to explain what is quantum communication, I would explain it in this way. Let's suppose there are two people here, and this guy sends a certain communication or certain message to this guy, and the message travels and then it reaches him. But let's suppose he sends the message in this state of 0. What is 0? 0 is 1 and 0. So here there's something two things we will involve: quantum coherence. Okay. Let's suppose if this symbol is said, when this signal is sent or this message is sent, quantum coherence, we want the quantum coherence to happen. This should happen. Okay, what I mean by happen is that when quantum coherence is there, the message is not intervened. Mean there is no third person. Okay, meaning if this code is sent, let's suppose 0 and 1, and to decode it we need to use Hadamard gate. Okay, and what is Hadamard gate? It is 1 1 1 minus 1. Okay, so this is a vector form of Hadamard gate. What is 0 and 0 in a Hadamard or vector way is 1 over 0. Okay, so let's suppose he sends this message to this person. When he receives it, and when he applies the Hadamard gate to this 0, what will he get? He should get 1 0. If I solve it, 1 1 1 minus 1. Oh, here, now look what will happen. 1 1 1 plus 0 1 1. Sorry, not 0 0 1 the 0. 1 1 the 1. 0, this is 0. So what do we get? What do we get? We get 1 and 1. 1 1. Okay, now This shows that the message is not interrupted. Interrupted, so on. Okay, so this is what you quantum coherence, that the information which is sent in a way that no information is lost, no information loss. There is no information loss. Plus, if the message is intervened from, let's suppose in middle someone, there's a third person, so the message will be interrupted. It will be the receiver and the sender, they both will know that in the message is interrupted. Okay, so in terms of in quantum coherence, we can say that the message is sent fully and is secured as the message is not seen by third person. What will happen? This will work if no communication is lost. Information, not communication. Information is lost. No, information is lost. More secured. But when we look at the scenario, what if there is a third person? This is sad, but the message intervened in the middle by this person. Alright, he sees it. Okay, now what will happen? He knows that 0. Okay, now when we always know that 0 and this, when applied with Heidelberg gate plus this 1 over 0, what do we get? We get 1 over 1. So that means message is seen by third person. So when this guy, when he will do it, when he will now decode this message, 1 over, this is actually positive. This is positive. This is not 1, it's actually positive. Okay, so when he will apply this to Hadamard gate, look what he will get. H plus Hadamard gate. This is not what we need. Okay, 1 1 1 minus 1. 0 when transferred makes, or transform makes plus. Plus is one way of saying positive. Okay, 1 and 1. 1 ones are 1, and then 1 ones are 1. 1 ones are 1. 1 times minus 1 is minus 1. So what do we get? What's our end result? It is 1 and minus 1. Not minus 1. 1 and 0. Now look, it's the same answer. 1 0. This proves it that the message was seen by a third person and that the message is now decoded by someone else as well. And this is called quantum decoherence. And we don't want to have quantum decoherence. Okay. Okay. So then what else can we say? What else? This is where information is lost before the receiver receives it. Okay. Then if I want to say what is quantum decoherence in proper way, I can say quantum decoherence is the process by which a quantum system loses its information, quantum behavior, and transitions into classical behavior. So, quantum decoherence, what is it? It's a process by which a quantum system loses its information or quantum behavior. What I mean by quantum behavior? Okay, what I mean by quantum behavior. We all know that quantum physics, in quantum mechanics, particle is both wave and particle. Okay. So when we don't observe it, means no one's looking at, no one's receiving it, no one is sending it, it will act as a wave. It will be acting as a wave. But when someone sees it, it will act as a particle, a single dot particle. That's what it means by quantum behavior. This is quantum behavior as someone is observing and someone is not observing. Okay, transition. Okay, typically due to its interaction with environment. So here there's a word they use is environment. Environment. In quantum mechanics, particles can exist in a superposition. As I told, this is one of them, and there's one more superposition that they exist in multiple spots at once. This is superposition. Okay. Then. Okay. Then. However, when a quantum system interacts with its surrounding, like air, molecules, photons, or other particles, it gradually loses its superposition. It's the advanced way of saying that the process superposition is finished. Superposition. Here we can say environment is the observer or the receiver or the third party. While decoherence explains the apparent collapse of quantum superpositions, it doesn't completely solve the measurement problem. In quantum mechanics, which addresses why only one outcome is observed, decoherence is, however, crucial for understanding the transition from the quantum realm to classical realm. So, it could be said that quantum realm is broken into classical realm. Okay, so then we will talk about quantum coherence also in detail. What is quantum coherence? Yes, as I've told you that quantum coherence is when we want to maintain the quantum nature, which is wave-like nature, as we don't observe it. It's how the system works in quantum physics. Till you don't observe it, it's a wave. It won't act as anything else but a wave. It will be in superposition state. It will be a wave. It will have all weird phenomena which it can have. Okay, allowing it to exist in a superposition of different states. Because when we talk about wave, and the best thing in how I can explain is superposition is that imagine the wave interaction, the Young's experiment, that if there's a electron gun and it shoots electrons, and we don't observe it, it's a wave, right? And when it goes through slits, what will happen? It will become a wave. It's right now, I would say it's like a straight wave. It's like a straight wave, like this. Now then after that it curves, and then when it goes through two curves like this, what happens that it makes two waves over here and here. So when we talk about this part here, this is something known as interaction. Interaction. Here, this is where the chances of finding the particle are more high. Chances of finding particle there. Okay, then well, this could be this is an example of Young's experiment. That's not that much. That's not topic. It's not a topic we should be discussing here. Here we can say okay, so then in to summarize, we say that the information transferred by given from this person to this person should is secured as quantum coherence and quantum decoherence plays a part. As if we don't disturb it, it will stay in quantum coherence state, and when we disturb it, it will become quantum decoherence, and then both observer and receiver will know that the information was leaked, it was seen by another person, third person, and then it's a way of knowing, we can say. The person will, I would say both person will know the information is leaked.